Hello viewers and welcome to another episode of Space Science with Python. Viewers, today we will conclude our multi-class classification problem with the Asteroid reflectance spectra. We will still stick with the topic for two more videos, or 2 or 3 videos, but today we will conclude the classification task. And last time we created our convolutional network before we created our dense neural network and so on. And well, if you create a neural network, the solution space is like determined by the architecture you created. So by the number of layers, by the number of neurons, by the number of filters or the kernel size for convolution network, also the max pooling size, and also the dense layers, maybe dropout and so on. Of course, as a human, you cannot even remotely grasp the possible solution space. So the solution space is, I would say, pretty huge. And by training the model, you find then the optimal solution in this solution space. But of course, an architecture cannot be really defined, or we don't know whether a solution space is like the optimal solution space of all available solution spaces. So yeah, there are like infinite solutions. We know certain best practices like convolutional networks are pretty nice for image recognition. We have also LSTMs or other recurrent networks for audio signals or speech recognition. There are some new architectures like the transformers. We have also separable convolutional layers also now, and so on. And of course, these are the best practices, so to speak, but we really cannot really know how the final architecture should look like. And for this, though, there is some way to optimize our, I would say, baseline architecture. And for this, we will use another tool called Keras-Tuner. The link is in the description of the Keras-Tuner, and we will also install it here in our Google Colab network. And of course, today's session is available on GitHub as always. Now, what do we do today? Well, we will simply re-execute mostly everything we already have, but we will not define a certain architecture or a certain number of filters for our convolution layer. No, we will provide a range of possible solutions, and Keras-Tuner will try to find the best solution for us. So it's like building up a huge solution space with the neural networks, but we will leave some parameters, let's say, open, maybe activation function, maybe the kernel size, and so on. Of course, we will still define a number of layers and so on. So it's, of course, again, some kind of artificial, I would say, squeezing and artificial constraints on the overall architecture. There are also some other algorithms like AutoML and so on, but you have to start at some point. Now, for this session today, we will need Keras-Tuner, which is not installed default on Google Colab, so we have to execute this command here, pip install Keras-Tuner, and we will use TensorBoard. So today we will have our first look on TensorBoard. Let's look at this a little bit later after the training. So again, Google warns us that it's some code from GitHub, but that's fine. We install everything. Actually, I just already installed it, so the requirement is already satisfied. These are the cells you know from last time, importing different modules, also reading in the data afterwards. I think maybe the warning will pop up. No, I already authenticated. And then, of course, our stratified shuffle split and also the one-hot encoding of the main groups. Now, one could even go a step further, and we could also do some k-fold training, like k equals 5 or so. But I would suggest to leave it as it is and just focus on our Keras tuning. And of course, our sampling weight. And now we are here in our model. Of course, there's still some artifacts from my training when I tried it a little bit out. But these are here the most important thing. We are importing Keras-Tuner. We are setting some early stopping callback. The number of inputs is defined. We have the normalizer here for our training data, and of course our first input layer and the normalizer that is being called here. Now, let's create our very first hidden layer. We will work again with convolutional layers, but we will not use them in a way we used it last time. We will not set like filters like, I don't know, 64 or something, but we will define a certain solution space. And here you see also here in this create model function, the input, there is some HP. That's like hyperparameter or so to speak. And this is something we will call later in our Keras-Tuner. So you will see, of course, there's now this HP is not defined yet, but you will see in a moment how this works. Now, first of all, for our filters, let's give it also a name. Let's call it the first filters. I would like to define a number of possible ranges that the Keras-Tuner should work with. So let's say we start with a number of filters of 8, the minimum and the maximum also, including this value here. It should called min and max value, 8 and 32, and then with a step size of 8. So it has a solution space from 8, 16, 24, and 33 to play around. So it's not really now strictly defined. Activation function, we can also set a different range, but yeah, I would suggest let's leave it with the ReLU functions to keep it also a little bit simple. And the kernel size can also be defined not interactively, but in a very dynamic way. And I call this here the first. So this is like only the naming. I call it the first kernel size. And let's also vary this value here between, let's say, 3 and maybe 7 with a step of 1. Yeah, so we call this here the norm layer, of course. So this is like our very first layer. And then we do the max pooling. And I would suggest to leave the max pooling though with 2 to reduce the number of parameters that should be trained later, because otherwise it may take a little bit too long. So max pooling 1D, we set the pool size of 2 and call the hidden layer. So this is our very first hidden layer, and our optimizer will later look at this thing here and see, okay, I can vary now the number of filters and vary the number of kernel size. So this is like the range the model can work with. Okay, so we can simply copy paste this, and I would suggest to create a second convolutional layer. We call it now here the second filters and also the second kernel size. And also we have to take care that we will call here the hidden layer, not the norm layer, of course. And of course we can also here vary a little bit. So we can say, okay, I would like to work here with a larger filter space between starting at 16 until 128 and a step size of, let's say, 16. So where's the cursor? There it is, 16. Yeah, and yeah, let's stick with the kernel size and also the max pooling. So this is like our second hidden convolutional layer. We are now flattening everything. So the hidden layer equals keras.layers.flatten, and calling the hidden layer, of course, hidden layer. And then afterwards we can create a dense layer. And also in the dense layer we can now set some range of possible solutions that the Keras-Tuner can work with. So let's call layers.dense, and then we say, okay, hyperparameter int, let's call it simply units. Min value starts at, I don't know, let's say 8, and the max value starts at or ends at 64 with a step size of 8. Okay, and then we can also create some activation function. And also let's stick with the relu function. And then finally, we have to call it as well. Just thinking, yeah, I should put it here. This is a mistake here, and removing this one. So this is how it should work. Hidden layer. Okay, cool. So another thing is also with the dropout, you may think, is dropout now, let's say, healthy or not? You can also create something which is called a Boolean, a Boolean decision. So sometimes the Keras-Tuner will decide whether to add the following layer or not. So you can dynamically change also the number of layers. You can also put a dense layer there, or maybe a third convolutional layer if you want. Just play around with these features and you're good to go. And also within the dropout, we can also vary the, let's call it, dropout rate, and starting maybe at a minimum value of 0.1 until max value of, let's say, 0.5 with a step size of 0.1. And also calling the hidden layer as well. So this is like an optional layer that is only being called occasionally and not all the time. So the Keras-Tuner will decide whether to use it or not. And now finally our output layer, the Keras layers.dense. Of course, this doesn't change at all. We have 4 classes. We use the activation function softmax because we have a one-hot encoding activation. Cannot really code and talk at the same time. Softmax, and then also calling here the hidden layer. And you see, since we call everything hidden layer, this here does not cause any problems. If we would have called it dropout layer or something, yeah, what would you write here? Hidden layer or dropout? This would be a little bit chaotic. So let's stick with the same naming convention all the time. And now we can create our Keras.models model, where, if you remember, if you recall already the previous videos, we have our inputs, which is simply the input layer, and we have our outputs, which is basically the output underscore layer. Now, very well, but I would say we will also compile it. So we will provide, calling the function will provide a compiled model, so optimizer, the Adam, and then we take the loss function, the categorical cross entropy, because we have a one-hot encoding. If you would have integers, it would be the sparse categorical entropy. Very well, I think we did it. Just executing it. Okay. And now we can create our Keras-Tuner. And Keras has 3 different ways to search for hyperparameters. So the first one, or the one we will use today, is quite simple and straightforward. You may know it already from scikit-learn. A simple random search. So it takes some random values here, plays around with it, checks the validation loss, and saves them, makes an early stopping at the lowest validation loss that we define in a moment, and then it stores all the models, and then you can simply see what is the best result. This is of course a little bit very brute force and quite simple. But there are also other optimizers. I think in total 3. The other one is, for example, the so-called Bayesian optimizer, and it works in a way that it tries some of these models out, the solution space you just defined, and then it tries to see, okay, where do I get the smallest validation loss, and then based on this model, it optimizes in a way to find the most likely, most probable model to optimize the validation loss more based on the previous results. So it's a little bit more, I would say, sophisticated, but for today's video, let's stick with the random search. You can simply replace here the random search by the Bayesian optimizer, and then it should work, I think. But there are also other input parameters that I will not cover today. Now, the objective is to find the minimum validation loss. So this is now something that the random search algorithm will take care of. You can also put the accuracy in there, or also other metrics, other loss functions as you like. So this is quite nice. So this is our random search, and now we define also number of epochs, so it shouldn't run into infinity but stop at some point, and also defining a certain batch size, so that now we can create our tuner or call our tuner with the search function. We put there X train and Y train, and you see it is pretty similar to the fit function of Keras. So it has basically the same input parameters like the batch size, like the verbose. So we will just suppress the output. Can take also the validation split. We will take it equal 0.25. Epochs also equals and epoch. Oh, I forgot a comma, I think. Yeah. And then, of course, the sample weight as well. Sample weight equals sample weight. And finally, our callbacks. And today, yeah, it's not a single callbacks. We will have two callbacks. The first one is the early stopping callback, and the second one is the TensorBoard. So we just loaded it in the very beginning, you may remember. And now we will use TensorBoard in a second to visualize interactively all our loss functions of this model search. So yeah, I would suggest let's get it running. And now since I already have already conducted the search, I already have some final results from the tuner from last time, which is stored under an untitled project tuner 0 JSON. I should have deleted it, so you can also name your project. I just left it didn't give it a name, just untitled project. Let me just quickly delete it. So I can't delete it, or what did he say? Delete folder. It's not empty. Only empty directories can be deleted. Okay, this is very unfortunate. Okay, so this is not a problem. Just give me one moment. I'll be just back and we'll delete this folder here from the command line and then rerun everything. So yeah, be sure that you're purge everything before start a new modeling. Otherwise, it takes the old results. So just give me one moment. I'll be back in a second. Okay, I'm back and I just deleted the folders. For those of you who would like to know how to do it, I don't know if this works with Colab free, but in Colab Pro you have the access to some small terminal, and the terminal I just wrote rm-r and then the folders, and then I just deleted it from the command line. So now we can conduct our learning, and now we have error here, categorical, cross entropy. So now it also spawns some errors, which is, I would say, good. So we know that it will run in a moment. And now it says, okay, it's now starting. And of course, it will also create our folders we saw just a moment ago. This may take some time. On my local machine, it actually was quite fast. Here on Google Colab, it depends a little bit on the resources you have. I think I'm running everything on CPUs now. So yeah, let's wait until the training is finished and then we see the final results. So I'll be back just in a moment when everything is done. And viewers, we are back. Our tuner is now finished. So we executed 25 different models and we can now check our final model. And to get our final model, we have to execute a rather simple command. We just say model is equal tuner get underscore best models. And the best model is the very first one, 0. So let's take it and we will work with it just in a second. Now you can also check the results from the tuner by simply calling tuner results summary. Default output is a little bit chaotic. You see here the different solutions. with the score and so on. Yeah, I will not go through it now. It's a little bit chaotic. You see different whether it was used with dropout or without, number of units for our dense layer, filter, second filter, kernel size, and so on. So all the huge combinations that have been chosen randomly and that have been tested. Now our model itself, let's just check it out, how it looks like. Yeah, okay, this is our final model here with 75,000 free parameters. And these are now the input layer 49, as we know. And then our first convolutional network, the max pooling, then again a convolutional network, then again max pooling, then flattening, and then the dense layer here. 56 neurons have been chosen in this case, and this is now our final model. And let's see whether how this model performs. But before we dive into it, I would say, hey, let's take a look at the validation loss and so on. And for this, we will use TensorBoard in a moment. And TensorBoard is quite mighty, so there are a lot of features. We will just take a look at the validation loss. So maybe TensorBoard is something for a future video. But here in TensorBoard, we have different IDs for our models. So to get our best model, we have to check for the so-called trial ID so that we know what is the best model. Model number 20 is the best model that performed perfectly. So let's call the TensorBoard. So you just write this percentage character, and then without any space in between the TensorBoard, and then log dir logs. So the logs have been stored. Now we can execute it, and I think it takes a little bit until it builds up. Yeah, now it builds up, and we go here to time series. And here we have now our epoch loss, we have the evaluation loss versus iteration and so on. So we have different metrics here that we can check. So it's a little bit small here, and we can now simply check out our different models. So here the epoch loss, for example, model 20 performed best. So let's take a look how the curve looked like for the validation. And let's put the smoothing a little bit down. So this is like our validation curve. We can then compare it, for example, with model 18. And you see model 18 was not so good as the other one. We had an early stopping, of course, so maybe it could have improved, but the early stopping prevented it from training further. Model 16 is also slightly above. 15, you see here. Let's take maybe the 10. Oh, there's also a spike here. So, and you can also, of course, plot all the models, I think. But this is very chaotic. Yeah, let's leave it like this. So you see, the difference is not that huge. So yeah, it's just small per mil or so that is being better. But well, it's based on the facts we have here in hand, it is our best model. And now we can, of course, plot again our confusion matrix and our F1 score as last time. I have it in the clipboard, so it's the code you're already familiar with, calling the confusion matrix display and also computing the F1 score. So let's execute this script here. And we have here our result. So the confusion matrix looks pretty nice, I would say, with only a few false classifications here, but only a handful, so pretty nice. And the F1 score is also pretty good with 0.97. So I think with the dense layer we had 0.91, I think. And with our convolutional network, with our, let's say, human set or manually set values, we had 0.94 or 5. So yeah, we improved it a little bit more with our Keras-Tuner. And of course, we can improve it even more. We can use the Bayesian optimization. We can use here the GPU power maybe, and make more trials to run through. But all in all, I would say we achieved a pretty fair result, pretty good, I would say, for this small project. And yeah, So what's the summary and our outlook? Well, I would say let's conclude the classification task with the spectra. I think we are done now with this one. But I would like to stay a little bit with the asteroid data. So some of you wrote that, yeah, maybe the next project I would, step back a little bit from machine learning and do something or show you something about near-Earth objects. But I still have some content for the asteroid spectra, and I think the next videos will be also quite interesting. So I think 2 or 3 videos with the asteroid spectra, we will tackle autoencoders. So pretty amazing topic. I will not spoil you now, but I hope you stay curious and enjoyed also today's video. If you know anybody, students or so, who can work with the material, feel free to share the content with others. And of course, I'm always looking forward to any comments and messages from you guys, either here or on Twitter. So until next time, and see you next week.